So thanks for taking some time of your lunch break for me. So I'm Dominic. I'm part of the growth team at DFINITY. I'm a solutions architect. Hello. Mainly helping ecosystem teams to build on the internet computer. And today I want to tell you a bit about, or give you a mental model about the internet computer, but more importantly about this chain fusion technology that we have, and how you can leverage it as an Ethereum developer or actually as a developer on every chain. So, and to start to give you a bit on a mental model about the internet computer, so as usual with a layer 1 blockchain, it all starts with the network. And already there, the internet computer is quite different than the usual layer 1. So instead of having people running their nodes at their home, or mostly actually on cloud infrastructure owned by big tech, the internet computer is built up of a sovereign network of standardized hardware run by independent node providers in independent data centers all around the world. And the internet computer protocol, which also involves an on-chain DAO, basically builds up of those individual nodes, builds them into subnets. And these subnets run canister smart contracts. And you see these multiple different networks that can be different in their topology, so different numbers of nodes to give different latency, but also different security. Still, the internet computer protocol weaves it all together that for an application or for you as a developer, it's completely transparent. So it doesn't really matter if your smart contract calls another smart contract on the same subnet or on a different subnet. And it all feels like a big computing environment. And it's much better to think of canister smart contracts as cloud functions or even virtual machines instead of thinking them what you can typically do with smart contracts. And the real difference to the normal cloud functions running on GCP, AWS and so on is now that you can have really autonomous functions. They can be DAO controlled or they can be even user controlled. And here you can see a couple of features of these canister smart contracts. To single out a few, so it runs WebAssembly, which means you can use all kinds of programming languages you are already used to. So many people use Rust, also TypeScript is used, and we also have Motoko, a programming language purposely built for the internet computer. You can host your websites inside canisters, and you can run long-running processes, even AI inference on-chain, and you can call out into the internet. So you have a connection to the internet directly built in. I want to give a very, very brief comparison with Ethereum. It doesn't matter too much, but one difference is, so most blockchains are synchronous, which means you lock state the whole computer basically for every transaction. The internet computer is designed from the beginning to be scalable, like a cloud, horizontally scalable, so it's asynchronous by nature. And this is sometimes to build DeFi a bit of a headache, but if you think of the internet computer as this platform that interconnects all the chains, then you have to be asynchronous because those communications with the other chains, not only the internal subnets of the internet computer, this will be definitely asynchronous. And the other big difference is, so Ethereum is highly replicated, right? And on the internet computer we have these node providers that go also through some kind of KYC-like process, so they are known entities, and they can be, by the DAO, if they don't behave, can be extinguished from the protocol. So we can have what we call deterministic decentralization. So we know that each subnet, you don't have to replicate it thousands of times. It's enough to replicate it maybe 50 times, and you have those node providers independent and in not a single jurisdiction. So, and now I want to go a bit on how the crypto behind that enables the seamless communication. So every subnet on the internet computer has what we call a chain key. So this is a BLS threshold key, and all state and all messages are assigned with these threshold keys. And the internet computer originated from a single subnet, the network nervous system root subnet, and all additional subnets got also a delegation from this root subnet. So what this means is subnets can easily talk to each other because they sign all the messages between the subnets with this threshold key. And the other subnet only needs to verify this signature plus the delegation from the root subnet. And this also enables super efficient light clients. So because a light client just needs to know this one public key of the internet computer to verify everything. So you can have like a client easily in your web browser, in your smartphone, in your IoT device, and so on and so forth. So okay, we have this cool chain key tech, but it turns out BLS signatures are a bit expensive to verify, and most of the other chains don't have pre-compiles for these BLS signatures. So when we think about how do we weave the rest of the Web3 ecosystem into this fabric of the internet computer, BLS is at the moment not the right choice, but let me now go a bit more into this chain fusion tech stack, which comprises chain key signatures, which we will talk about, and network integrations. So the internet computer doesn't only support BLS threshold signatures, it also supports ECDSA and since recently Schnorr and EDDSA threshold signatures. This allows smart contracts, canisters on ICP, to natively sign transactions for most of the blockchains out there. So you can control smart contracts on Ethereum, you can hold Bitcoin, you can hold Solana, you can interact with the Solana network, and so on and so forth. And what's nice about threshold signing is the signature that is generated really looks like a regular signature created by a normal EOA. So it's very easy for another party to verify those transactions and signatures. It also allows the internet computer to have this dynamic node set. So every couple of hours, basically, those key shares that are used to generate these threshold signatures are reshared within the network, and so you can have new nodes joining, nodes leaving the network, but the key still stays the same. And this also adds security, because if an attacker attacks a certain number of nodes to extract those key shares, they have to do it in this small window of a couple of hours. So yeah, I mentioned, so ECDSA has been around on the internet computer for a long time. We built like this Bitcoin integration on top of it. And since recently, we also have Schnorr signatures, which allows you to, for example, mint ordinals on Bitcoin and many more, and EDDSA, which allows integration with Solana, and if anyone cares, also Cardano. And so now we have seen how we write to those other chains, like the communication between the internet computer outgoing. But we also need to like really talk to those other nodes and also get state from the other chains to have bidirectional communication. And that's why we have these network integrations, and we have two ways at the moment. So the coolest one is definitely the direct network level integration, and we've built that for Bitcoin. So some of the nodes on the internet computer also run part of a Bitcoin node as a site, so to connect really to the Bitcoin on network, on a peer-to-peer layer. And then you have essentially a light client running as a canister on ICP, which makes at the moment, for example, the whole UTXO set of Bitcoin available to all smart contracts on ICP. And we are currently working on to also have all the raw blocks available. So you can build like a decentralized block explorer and later on also decentralized indexer of Bitcoin meta protocols like ordinals and runes and so on and so forth. For all the other chains, we go a bit of a different way. So I mentioned that canisters can do these HTTP outcalls, which means they can call web APIs. And it turns out you can use this also to integrate with other chains by just calling a couple of like institutional RPC endpoints out there. So you call Anchor and Infura and whatever, and only if like a quorum of them gives you the same result, you trust it in your canister. And we've built quite a bit of tooling around that, so an EVM RPC canister to make it really easy from canister smart contracts to talk to EVM chains. There's also a work in progress on a Solana RPC canister, and people have built like an integration with Cosmos and so on and so forth. Yep, I've already said that. And because we use WASM as an environment, and you can use Rust or TypeScript, you can also in most cases just use the libraries you're already used to. So for example, Ethers RS or Alloy or Rust Bitcoin directly on the internet computer. And currently, one of our engineers is like looking into making it even easier, so integrating like an ICP signer and ICP provider into this very popular Alloy library, so that you really have a very smooth flow here to sign a transaction on the internet computer with this threshold signing from a canister, and the same could be used to sign transactions. And this is an example from this exploration to get a balance of an Ethereum address from the internet computer. It's also just a couple of lines of code and very similar to what you're already used to. So let's get a bit into what can be built on top of that. And I don't want to talk too much about chain key tokens. These are projects that currently the DFINITY Foundation has built. These are those non-custodial wrapped assets. So you have a version of Bitcoin on the internet computer, and you have a version of Ethereum and a lot of ERC20 tokens, and you can make a proposal to add ERC20 tokens, and then you have this non-custodial representation on ICP, which can then plug into the whole internet computer ecosystem. It's very fast, very cheap, and so on and so forth. And there are already projects who are now exporting those tokens to other chains again. So a lot of Bitcoin layer 2s are served by the internet computer with Bitcoin, with CKBTC. And there was also recently this announcement that Omnity, a team, brought BTC to Osmosis, also via the CKBTC route on the internet computer. Yeah, and there is a lot of stuff that is being built. So people build like lending protocols on Bitcoin using ICP. They build non-custodial web wallets because you can use this threshold signing obviously also to serve end user accounts. People are building co-processors for Ethereum smart contracts and oracles, and so on and so forth. I want to go into a couple of in a bit more detail. I do have a bit of time. So one thing, together with the CK tokens you can experience at our booth outside, is this Oisi wallet. It's one of these non-custodial web wallets. So you can log in from multiple devices using passkeys, essentially. And it's a wallet that works for the internet computer. It works for the Ethereum ecosystem, and we will soon also support Bitcoin, and I assume also Solana. And yeah, you don't need to download anything. It's, from that perspective also, you have plausible deniability if you ever get into security controls or, I don't know, attacked by someone, because it's really just a website. Then another fun example is C-Cloak Network. They use the internet computer as a verification layer for all kinds of zero-knowledge proofs, and then teleport the verification results to all kinds of EVM and non-EVM compatible chains. And what I want to show here is they have this little example which shows you that you can build experience for all kinds of chains on the internet computer, and users don't even notice that there's the internet computer involved. So this website is hosted on the internet computer. You log into with an EVM wallet or with a Solana wallet. So the internet computer has this native account abstraction at its core since 3 years already. And then you can move this character through that maze, and then you generate client-side a proof of how many turns you took, so how many steps you needed to fulfill that maze. So you prove that you did it in a certain number of counts, but you don't show the way, and then this proof is submitted to the internet computer, verified on the internet computer, and then teleported to the destination chain using threshold signing. Another one that I like quite a lot, which is also an example of this, people don't even know that they're running this on the internet computer. You probably know about the Ethereum attestation service. It's like a service and a protocol to have on-chain and off-chain credentials, so kind of verified data about certain things. And this CATS project, Composite Attestation Service, allows to create rules on like fetching different kinds of attestations from different chains, from off-chain sources, and then computes on that composite attestation, like computes on this set of attestations and creates a new attestation out of that and makes it available for EVM chains again. And to make this easy and simple, the developer even like ported a JavaScript interpreter on the internet computer, so he can have these rules on how to mingle these attestations and how to combine them together on the internet computer, and then uses again threshold signing to port this composite attestation to the end chain. And also here you just connect with your Ethereum or EVM wallet, and you don't notice as a user that the internet computer is involved. So, and I think we've only really scratched the surface here on what's really possible. So I invite everyone to check it out, some of the things at our booth, but also get in touch with me to discuss about use cases and get involved in the community and start building on the internet computer. So with that, thanks a lot. And